The goal of this video is to get you thinking about radar data, what a radar is, why we collect radar data in glacier systems, and ultimately how are radar data structured. I think that's a particularly important point to make before you start working with the data yourself. So this image here is a photo of me with a ground-based radar system in a place called Hercules Dome in central Antarctica. And this is a multi-channel coherent radar system. It produces data just like the data that comes out of NASA's Operation Icebridge, which is the primary radar data set that I spend my time thinking about. Before we dive into the specifics of how radar data are analyzed, I want to present this model of the radar problem. What you see on the screen, this left panel, you can think of like a cross-section of a glacier system. The y-axis is depth, so up at the top is high in elevation, down at the bottom is low in elevation. The x-axis is distance, so we've taken a slice through a glacier. And the little black asterisk up in the top middle of that plot, that represents me, sitting at the surface of the glacier with a radar system. In a second, I'm going to set this animation in motion. But what happens is that radar sends out a pulse of electromagnetic waves. Snap. Out goes the light wave. As that wave propagates into the subsurface, it encounters electrical contrasts, and every time there's an electrical contrast, some of that energy is reflected back towards the surface. Meanwhile, the radar, sitting with me, is measuring the strength of the electromagnetic field locally. So after that initial burst of energy goes out, the electromagnetic field is pretty quiet, and then we start to get these echoes, these reflections, that arrive at the system, and we see these perturbations to the electromagnetic field. So that plot on the very far right is going to be a time series, and it's measuring the strength of the electromagnetic field through time. So let's hit play and see what happens. So we send out that radio wave into the subsurface. Anytime it encounters an electrical contrast, a little bit of that energy is scattered backward, and you can see that some of that energy is passing by our system and being measured in the wiggles on the right. Now, the biggest, I wonder why that happened. The biggest electromagnetic contrast is between ice and rock. And so at the very base of the glacier system, if this video wasn't busy getting corrupted, we see this big bright reflection. That's right here. That reflection is the reflection off the base of the glacier system. If we know something about the speed of light in ice, and we know what the time is between when the radio wave was sent and when the radio wave is received, we can measure the thickness of the ice. So we get some first order information about the structure of the glacier. Not just the full ice thickness, even though that's the easiest thing to measure, we also get a bunch of information, about the interior structure of the glacier. So radar is this really powerful tool. If we, I'll stop that. If we collect a bunch of these time series at sequential locations along the surface of the glacier, we start to assemble this two-dimensional picture of what the subsurface looks like. So here are those reflections off the ice bottom. We have some reflections off the interior of the ice column here. We have the initial transmission. So we get this beautiful cross-section of the glacier. Now, if you imagine we only had a single radar antenna taking a measurement, I've diagrammed here this representative plane wave coming up from below towards our antenna. We have no way, if we only have a single measurement, of telling the difference between that wave coming from below, this wave coming from in front of the system, or this wave coming from behind. And so we can't tell immediately whether or not the source of the reflection is straight below us, if it's from in front or from behind. So one thing we do when we're collecting radar data, as I mentioned before, is we collect this sequence of observations. We take a measurement here, we move forward, we take another measurement, we move forward, we take another measurement, and move forward. So if, for example, the thing that's generating the reflections is over here, then we get this set of responses that take a different amount of time to go down into the subsurface, reflect, and come back up when our instrument is at this location than it does when our instrument is at that location. And so what we do is we fly our plane along over a glacier system, or we drive our radar system in a snowmobile over the glacier system. And by taking these multiple measurements, now we can start to tell the difference between waves that are arriving from behind and waves that are arriving from in front of the instrument. So when we collect data and we just stack up each of those individual time series, we assign the strength of the electromagnetic field a color, and we plot all of those time series right next to each other, we get an image that looks like this, where our y-axis is the amount of time it took for the radio wave to leave the system, reflect off of something, and come back, with more time as we go further down the image. Our x-axis represents that distance, again, as we fly our plane or we drive our radar along the surface. And we can see the internal structure of the glacier system. We can see the reflections off the bottom. One thing that you'll notice is that the reflection off the base of the glacier system has these characteristic little hyperbolic shapes. You can see things that look like this everywhere in the radar image. We see things that look like that because targets that are just a little point, they get measured when our radar system was here at the surface and measured here at the surface and here at the surface and here at the surface and here at the surface. We see that same source of a reflection at multiple locations. And so the first step in analyzing radar data is to take that sequential information, the information from our first acquisition, our second acquisition, our third acquisition, and use it to do something called synthetic aperture focusing. So we create a focused image by integrating information across all of those separate acquisitions. And I'm going to step forward and you're going to see the focused image. There's the focused image. Unfocused, focused, unfocused, focused. And so we've taken those sequential acquisitions, and now we can see all of the details. Whoops, didn't mean to do that. We can see all of the details associated with the scatterers at the base of the glacier. All of those things came into focus. Okay, so if we're working with radar data, what does it look like? Typically, radar data is stored in a big matrix, where every cell in this matrix is a value, and those values represent an observation of the electromagnetic field. So each row in our matrix represents an amount of time after the transmitted pulse has been issued. So this, for example, is time 0. That's when our transmit pulse is triggered. And every sequential observation as we move down is listening a little bit later in time for the strength of the electromagnetic field. This process happens very, very quickly. The speed of light in ice is about 168 million meters per second. It's very fast. So typical like delta time, if we were to go from 0 to our first delta t, 2 delta t, 3 delta t, the time between measurements of the electromagnetic field, that's on the order of nanoseconds, 10 to the minus 9th seconds. And so we often call this axis in radar data, the rows or the vertical axis, we call it fast time. Because the amount of time between each of those individual measurements is tiny. Now, this column of observations represents the measurements taken from a single radar pulse, effectively at a single location at the surface of the glacier. When we move over to that next column, we've moved our whole radar in space. We send out a new wave and we listen. And as we listen, we fill in another column of observations. We listen in fast time, we carry our whole radar system forward another step, we listen, we collect observations. Typically, each of those radar transmissions happens on a regular cadence. So we take one, we listen. We step forward, we take one, we listen. We step forward, we take one, we listen. And there's a fixed amount of time between each of those transmit pulses. But that tends to be much, much, much slower compared to the rate at which we're observing the strength of the electromagnetic field. Like maybe hundredths of a second or thousandths of a second between our first observation, our second observation, our third observation. So often we think of this x-axis, or the columns, as what we call slow time. Because the time between pulses is very long compared to the time after the pulse that we're listening. Again, you can also think about these axes for the physical coordinates that ultimately they represent. We can convert fast time to depth in the glacier. We can convert slow time to distance along the glacier system. But ultimately, we have all of these measurements of the electromagnetic field at the radar instrument stored in this big matrix. And so typically we'll have a matrix that maybe we'll say we have n samples in fast time, m samples in slow time, and therefore the radar data are a big n by m matrix. N rows, m columns. Associated with the radar data are a bunch of important ancillary data. So for example, we may have GPS coordinates for our radar system at each of these observations. So there may be an object that's 1 by m, as in we have m observations, one for each of our slow time samples, that represents, for example, the GPS coordinates in latitude and longitude. Maybe we also have like the time that radar pulse was triggered. Maybe we have the elevation of the plane. All of these we would expect would be objects that are 1 by m in size. We likely also have an object that describes exactly how much time has passed between each of our samples in fast time. This tells us basically the time that we were listening after each pulse. And that object that stores those times might be a size 1 by n. We have n observations, or n defined time samples that correspond to our fast time measurement. So it's important to recognize that this is a pretty typical structure for radar data. The data themselves are stored in a matrix, and there are these vectors that are either m or n long that are the metadata associated with those observations. Ultimately, we have an equation that describes the nature of the radar reflection problem. We fundamentally measure the power at the radar system. We're measuring the strength of the electromagnetic field, which we can describe in units of power. The power that we get at the instrument, the power that we measure at the instrument, depends on a bunch of things. It depends on how strong the transmitted power was. If we send out a really loud electromagnetic pulse, then we'll get a loud reflection. Quiet pulse, quiet reflection. It depends on the antenna and how well the antenna can measure the electromagnetic field. It turns out that the glacier acts kind of like a big lens, focusing the light downward. And so, depending on the thickness of the glacier and the structure of the near surface, that lens could focus the energy a lot or a little. And so, one of the things that affects how much energy we get back is this term we call the refractive gain. It's the focusing of that light in the subsurface. If you look at all of these terms, what you'll notice about them is that none of them depend on how far away your target is. Oh, actually, there's one other term that is important in here that I want to mention. This is in some ways the most important term. This is the reflection coefficient. And this is defined by the contrast in the electrical properties. There's this property called the dielectric permittivity. It controls the speed of light in ice. The contrast in the permittivity between ice and whatever the second medium is that's generating the reflection, that contrast controls how bright a reflection is. If they're really different, then all of the light reflects. If they're very similar, then there's very little light reflected back at you. But importantly, none of those terms depend on how far away your target is. There are some terms that do depend on how far away your target is. This term, the geometric spreading term, says that when we send out a pulse, we're sending energy out in all directions. And so as that pulse gets further and further and further away, that energy is less and less and less concentrated, because it's essentially concentrated on this spherical shell that's spreading out and getting bigger and bigger. So if our target is further away, we get less energy back because it's spherically spreading. There's also this other important term that's labeled here attenuation. This term represents the loss of energy to the medium through which the wave is propagating. So it turns out ice can conduct an electrical current. It's not a very good conductor. In fact, it's a pretty poor semiconductor. But in the presence of an electromagnetic field, some of that light wave actually generates a current in the ice, and it's carried away like an electrical current is carried by any other material. And so we're constantly losing a little bit of energy to the ice itself. We call that attenuation. It turns out the ice's conductivity depends on its temperature. And so one really interesting thing we can start to do is look very carefully at the power that we're measuring at the radar system. Because the amount of energy that's lost as the wave propagates depends on the temperature of the ice, we can start to maybe tease out differences in temperature that manifest as differences in the power that we're measuring at the instrument. So how do we do that? Well, we have to disentangle two fundamental unknowns. As we said, the strength of the reflection in part depends on the material that's generating the reflection. So if I send out a wave into an icy body, and that wave hits an interface that's either frozen till, unfrozen till, water-saturated till, or just water, those all have different reflection coefficients. Water being the brightest reflection, frozen till being the least bright reflection. So if we want to start to interpret the power that we're getting back at a radar, we have to make some assumptions or have some other constraint on what material is generating the reflection. As I said before, temperature really controls the conductivity of ice. So the reason that's the case is because ice is this nice hexagonal crystal with these H2O molecules all bound up within it. The way that ice conducts a current is by actually the motion of protons, the motion of hydrogen atoms through the crystal structure. And the warmer the ice is, the more defects there are in the crystal, and the easier it is for these protons to flow. So if we send out an electromagnetic wave into very warm, impure ice, if we send it out into ice that's just at the melting point but pure, or ice that's very cold, what we see is that when a wave goes out into ice that's very cold, more energy comes back to us, because less of it is lost to current in the ice. If we send a radio wave out into very warm ice, then more energy is lost and we get less back at the instrument. I also showed you in the radar images we looked at before that we could get information about the structure of the glacier itself. I'm going to play this animation. This animation represents the cross-section of a glacier system. So again, x is distance, y is depth. It turns out that as snow falls, it carries with it some signature of the chemistry of the atmosphere. So if the snow that falls is falling at a time when there's lots of impurity content in the atmosphere, let's say there's lots of dust or lots of sea salt or lots of acid in the atmosphere, that gets deposited with the snow. And it turns out through time, the number of impurities in the atmosphere change. And so as snow falls, every year the snow looks chemically a little bit different. And when it's chemically different, it's also electrically different. And so when we think about a glacier system, glaciers are built up of these layers of snow that fall year after year after year after year. What you're seeing here is the burial, deformation, and flow of layers within this glacier system. If we think about each of those layers as having its own chemistry and its own electrical properties, what that means is that each of those layers can generate a reflection when the radar sends out its light wave. This apparently projecting these things after a certain amount of time, the video gets unhappy. But what we have here is some evidence of two things. One, radar can measure the structures inside glaciers because we have these electrically different layers. 2, the layers that we see within a glacier system, because they form primarily by these depositional processes, actually record a horizon of constant time. We call those layers isochrons. So this is a layer where everywhere we see this continuous line in the glacier, that represents 1 year or 1 moment in time for that glacier system. So we can use the glacier to start to reconstruct the time evolution and the flow history. We can use the radar layering to reconstruct the time evolution and flow history of a glacier. There's one thing I want to point out that is important, although it's pretty advanced when we're thinking about radar systems. All those images I showed you before, they were collected along a straight line, and we were making an implicit assumption about the data we were getting back. We could focus it so we could tell the difference between something coming in front of or something coming from behind us, but we had to assume that nothing was coming from the left, nothing was coming from the right. That after we did our focusing, all of the reflections we assumed were coming from right below the instrument. That assumption is not a very good one. Now, we can use some special techniques to do more than just focus the image down, but we can start to discriminate between reflections from the left of the instrument, reflections from the right of the instrument. So, imagine we're a plane flying along over a glacier system, or we're dragging that sled that I showed you on the first slide. This plane is special. It has more than one radar antenna. It has antennas spanning the wings. So the plane is flying out of into the page toward us. I guess that's out of the page toward us. And it's making measurements. If the source of a reflection is right below us, then we would expect that reflection, that reflected wave, will arrive at all of the antennas on our plane at the exact same time. If it's coming from the right of the plane, then we might expect that reflection arrives first at the antenna at the far right wingtip, and then will arrive slowly thereafter at all of the other antennas. If it's coming from the left, the reverse is true. It arrives first at the antenna on the far left wingtip, then the antenna on the far right wingtip. We can start to process radar data in a way that not only focuses in front and behind, but also discriminates, as I said, from the left or the right. And so this plot on the right is slightly different from the traditional radar images we've looked at. This one on the left is the same. Our y-axis represents that fast time or depth. Our x-axis represents that slow time or distance. But now, using this full antenna array, we can create an image for every single column in our radargram, where this image on the right tells us, did the energy come from the left? If it came from the left, it'll plot over here. Or did it come from the right? If it comes from the right, it will plot over there. And so you can think about this as a slice. And we can take lots and lots and lots of slices that are perpendicular to this image and start to produce a three-dimensional topography. So if I set this animation in motion, turns out this isn't an animation, but you can see that as we were to fly along, we get a bunch of these cross-track images that are showing us where we're getting reflections off the base of the ice from the left, where we're getting reflections off the base of the ice from the right. And we can start to, instead of just getting a 1D along track picture, generate this 2D swath map of the bed. So some of my most cutting edge research is really trying to update our maps of Antarctic and Greenland topography using this swath mapping technology. So for example, here are 2 subglacial bed elevation maps that were generated from old radar data in West Antarctica by traditional methods. We apply that swath radar technique and we can generate images that look like these. It's actually, I look at these all the time, and every time I'm amazed. I think they're so beautiful, and they give us so much information that we didn't have before about the subglacial environment. So hopefully you have a sense now how radar is this wonderful tool for studying the subsurface, and you have a little bit of a better understanding of the structure of the data and how we might start to work with it.